Hey guys, welcome back to my channel. So today let's talk about the Snell's law. So as you can see from the box, this is the equation for the Snell's law, and now let's break down each component. Okay. All right. So imagine I have some fresh light, some light resource from the bottom of my water, and then this gives a ray of light that hits the surface of the water. Okay, and then when it hits the surface of the water, it has two options. The light can either reflect or refract. Okay, so if it was a mirror, it would definitely reflect the light. But in this case, the light can also do refraction. So we're going to talk about the case of a refraction first. Okay, all right. So before the light refracts, let me draw a line that is perpendicular to the surface where the light is hitting. Okay, that is the surface the light is hitting, which is horizontal, and then this vertical line is we call it normal line. Okay, that's perpendicular to the surface. All right, so the angle between the normal line and the light of incidence we'll call theta 1, which is the angle of incidence. Okay, so on our equation, this is theta 1 here, and then this is theta 1 here. Okay, all right, so now let's refract the light. Okay, so when we refract the light doesn't just go like that, a straight line, right? It will kind of bend. Let's say it bends this way. Okay, so it bends this way. So now the angle between the normal line and the refracted light is theta 2. Okay, theta 2 here and theta 2 here. Okay, so how do I know if theta 1 is larger than theta 2 or vice versa, right? So according to the equation, that depends on n1 and n2, right? Because for these two parts to equal to each other, if n1 is larger than n2, then theta 1 has to be smaller than theta 2, right? For this to balance. All right, so n1, what is n? So n1 is all the n's are called refractive index, or the index of refractions. Okay, so in this case, the water's refractive index is 1.3. Okay, 1.3, and then the air, N2, its refractive index is 1. Okay, you have to know this for MCAT. Memorize the refractive index for air is 1. Okay, other mediums refractive index will be provided most of the time. Okay, all right, so now we know that okay, N1 is larger than N2, right? According to the data I just provided you. Then this tells us that sine theta 1 must be smaller than sine theta 2 to make this Snell's law established, right? And then that tells us that theta 1 must be smaller than theta 2. In other words, theta 2 must be way larger. I mean, not way larger, but larger than theta 1, right? And then this is the case that I drew for you, that theta 2 looks larger than theta 1, okay? All right, so here I want to mention one more thing about the n. So the n actually, the mathematical equation for the refractive index is n equals c over v. Okay, so c is the speed of light, which is 3 times 10 to the 8th meter per second, and then the v is the velocity that the light travels either in water or air, and diamond and vacuum, or any medium, right? So if c divided by the velocity of light travels in water, then we get the n water, right? The refractive index of water. If we plug in the velocity of light travels in air, then we get the refractive index of air, right? All right, so as you can see, n is inversely related to the velocity, right? In other words, if a thing that travels super slowly, if light travels super slowly in a medium, then it means it has like a really relatively high refractive index. It will bend the light more, right? Okay, so mentally we want to know n1 over n2 is inversely related to velocity. Okay, so, and then also from, before I move on to the Snell's law, that we know wavelength is directly related to velocity. So this indirect relationship between velocity and wavelength gives us inverse relationship between the n and the wavelength, okay? And then the Snell's law very obviously tells us the theta 2 over theta 1, the inverse relationship between these factors. So just have this mental equation that helps with the calculation on MCAT, okay? All right, so now let's talk about the second scenario, okay? So as we see here that because n1 is larger than n2, so theta 2 has to be larger than theta 1, right? So if I increase the angle of my theta 1, let's say if now I shine the surface at this angle, then you see, oh, theta 1 is larger, but theta 2 has to be even larger than theta 1. So theta 2 will have to be really be increased, right? So like, for example, here, theta 2 is here, but you really have to like increase it more and more so that the theta 2 can be increased, right? So, okay, so this is the case for our second scenario, that I increased the angle of theta 1. Before I draw the theta 1, let me draw the normal line again. The normal line is fairly important, okay? Okay, so this is my new, let's say, theta A, okay? So I increased the theta A to an extent that my theta B, my angle of refraction, gets to 90 degrees, and this is my light of refraction. Okay, so when this happens, my theta A is called theta critical, the critical angle, right? And then to calculate the critical angle, we know this sine theta C equals n2 over n1, right? So the critical angle equals to arc sine n2 over n1. Okay, so that's how you calculate the critical angle, right? Because as theta 1 changes, theta 2 has to change, right? Because n1, n2, they're constant. They're constants. They're the inherent characteristics of certain medium, right? All right. So when theta 1 changes, then theta 2 changes accordingly, right? When theta 2 gets to 90 degrees, we call theta 1 theta critical angle. All right. So this is two scenarios when light refracts. Now let's the third scenario. Let's talk about the case of reflection when light reflect. Okay. So when now my light source shines the surface at a third angle, and then this angle is larger than theta 1 and then theta critical that we just talked, right? It gets larger than even theta critical, and then in this case you can see that my theta 1, my new theta 1 is here, right? And when it exceeds theta critical, it actually reflects. Okay, so light will reflect back to the water, and then here theta 2 here, theta 1 is equal to theta 2. Okay, and then this is called total internal reflection. Okay, and then for total internal reflection to happen, the one condition is your n1, I mean where the light source is from, n1 has to be larger than n2. Okay, the light travels from a denser medium to a less dense medium, and then total internal reflection can happen if your theta 1, aka your angle of incidence, is large enough, even larger than the theta critical, then this can happen. It doesn't happen when you travel from air to water or air to diamond, okay, or vacuum to air. No, not the case when it's going from less dense to more dense, only when it's more dense to less dense. Okay, which also, if you relate this equation, N equals C over V, we know that V1 is smaller than V2, okay? So light travels in water at a slower rate than it travels in air. Yeah, of course, because water is denser, right? All right, so that's the basics of Snell's law, what you learned from the physics class, okay? Now, for MCAT, let's apply it to some biological scenario, okay? So here, I have a problem for you, okay? So this is an eye, right? And then the light we see, the light that hits our cornea is from the air, right? Which means the medium N1 is air, okay? So light is coming from air, hitting your cornea, and then it refracts, okay? And then the liquid inside your air, whatever that liquid is, let's assume that N2 equals 0.8, which is less dense than the refractive index of air, okay? So the problem is asking you to choose, so A and B, okay? A and B. So choose the correct answer that reflects how the light would refract once it hits your cornea. Yeah. Okay, so I'll give you guys like 2 seconds to think about it, or you can pause the video and take as long as you need. Okay. So what do you guys think? So most students got tripped up and then they choose A. Okay, why? Because according to what we learned in our physics class, you can see that, okay, this is theta 1, right? The angle of refraction. And then my theta 2 is this angle, right? My theta 2, which is the case that we show here, okay? And then you think, okay, then this theta 2 must be larger than theta 1, and then this theta 2 from choice A looks way bigger than the theta 2 from choice B. So yeah, the theta 2 from choice A is larger than the theta 1 from the problem, so I'm gonna go with A, okay? Is this the correct? That is actually the wrong answer, okay? Why? Because like I said, the normal line is pretty important. And then when we talked about the water-air scenario, you have to realize our surface. Okay, I'm going to use a different color, okay, a green one. So we have to realize our surface is really horizontal. So this gives me the vertical normal line, right? But here, when the light is hitting our eye, even though our cornea is curved, but still my surface that the light is hitting is kind of vertical, right? And then in this case, my normal line, the line that is perpendicular to the surface that the light is hitting, is actually horizontal now, okay? So if that's the case, we know this line, this one in case is my normal line now. Not a vertical one, but a horizontal one. And then according to the definition, the theta 2 is the angle between the normal line and the refracted light. Then we'll know, okay, then theta 2, oh, geez. Theta 2 is this angle, right? And then this is theta 2. And then where is theta 1? Theta 1 is actually this angle instead of the angle here, okay? Yeah, so make sure you pay attention. What is the surface that the light is hitting? It is horizontal or vertical, and then you draw a vertical line, that is the normal line. And then you decide where's theta 1 and theta 2. Okay, so now after we remarked theta 1 and theta 2, you can see because N1 is, once again, not to sound like a broken record, but once again, since N1 is larger than N2, and then according to the Snell's law, all the interpretation we did here, we know that theta 2 has to be larger than theta 1, right? This inverse relation. So looking at theta 1 from the problem, then B is our answer, right? Indicating theta 2 way larger than, not way larger, but larger than theta one in an obvious way. Okay, all right. So this is the tricky part. Okay, I don't want you to get tripped up. Okay, now I changed the problem. Now my N2, the liquid in your eye is 1.5. Okay. All right, so I don't know what's the truth if the refractive index of our aqueous solution will be higher than 1 or 2, but I'm just like reflecting this the physics idea. I'm applying it to biological application. So I really just want you to drive home the point that when N2 now it's different, right? Okay, now N1 is smaller than N2, and now we need theta 2 to really be smaller than theta 1, okay? And then if we were to draw again our normal line, the normal line is this line, right? Is this line. And then my theta 2 will be theta 2, okay? And then which theta 2, A or B, is smaller than the theta A from the problem? It's answer A, okay? All right, so just be really good at applying the physics ideas, the concepts. Once you learn this from your physics class, you say, oh, I get it. Oh, it's easy. I know what is theta 1, theta 2. But if you forget the details, if you just miss one detail of now I'm hitting my eye and I'm a person that's standing up, it's being hitting vertically, so that changes the normal line and then changes the whole scenario, right? But if the person is lying down on a bed, let's say, and then you do some X-ray stuff, you shine the light onto the eye in a vertical fashion, then it's a different story. Okay, so just read your problem and then really just pay attention to the details. Okay, I hope that helps.